I'm standing here at 2,600 meters above sea level in the Atacama Desert of northern Chile, looking up at what will soon become humanity's most ambitious attempt to photograph the invisible. Behind me, the Vera C. Rubin Observatory rises like a gleaming white temple to the unknown, its 8.4-meter mirror preparing to capture light that has traveled billions of years through space, only to reveal nothing. Or rather, everything we can't see. The irony is almost poetic. Here we are, building increasingly sophisticated eyes to peer deeper into the cosmos, only to discover that 85% of the universe is playing an elaborate game of cosmic hide-and-seek. We can see its effects: galaxies spinning too fast, light bending around invisible scaffolding, the very structure of reality held together by something that refuses to interact with our instruments except through the most subtle gravitational whispers. Next month, this observatory will begin its 10-year survey of the southern sky, photographing the entire visible heavens every 3 nights with a camera containing more pixels than there are people on Earth. Its mission? To map the distribution of matter we cannot see, using techniques that would have seemed like magic to the astronomers who first stumbled upon this cosmic mystery nearly a century ago. You see, the story of dark matter begins with a simple question that turned out to have an impossibly complex answer. Why don't galaxies fly apart? It's the kind of question that sounds almost trivial until you realize that the answer requires reimagining the fundamental nature of the universe itself. And it began, as so many great discoveries do, with one scientist noticing that the numbers simply didn't add up. But I'm getting ahead of myself, because before we can understand how this gleaming monument to the invisible came to exist in one of the driest places on Earth, we need to understand how humanity discovered that most of the universe was missing in the first place. And that story begins not with sophisticated telescopes or billion-dollar observatories, but with a stubborn Swiss astronomer who refused to believe his calculations were wrong. Welcome back, my gravitationally bewildered galaxy gazers. I'm your quantum superposed dark matter detective, simultaneously detecting and missing the fundamental structure of reality across infinite cosmic neighborhoods. You're tuned into the Multiverse Employee Handbook, the only podcast that treats your search for invisible cosmic scaffolding like a particularly challenging game of multidimensional hide-and-seek, where 85% of the players have forgotten to show up. Gather round the quantum construction site, my architecturally anxious astronomers, for a tale that would make even M.C. Escher question his perspective on reality. In the fluorescent-lit realm of Quantum Improbability Solutions, specifically in the Construction Management Division, which existed in a superposition of ahead of schedule and catastrophically behind deadline, Chief Engineer Patricia Cosmos was having what could charitably be called a gravitational orientation crisis. It had started, as these things often do, with what seemed like a routine ribbon-cutting ceremony for the company's newest facility, the Cosmic Observation and Reality Verification Observatory, designed to peer deep into the mysteries of space and provide what the marketing department called synergistic astronomical insights for next-generation cosmic engagement metrics. Patricia arrived at the construction site with her hard hat and ceremonial bolt cutters, only to discover that the $47 million observatory had been built completely upside down.
Oops.
The massive telescope dome sat firmly planted in the ground like a metallic mushroom, while the foundation jutted skyward like an inverted concrete wedding cake, complete with rebar garnish. "How," Patricia asked the foreman, "did you manage to build an entire observatory with the telescope pointing directly into the Earth's core?" The foreman consulted his blueprints, rotating them 180 degrees several times. "Well, the plans did say groundbreaking astronomical research," he offered hopefully. "We just took it literally." Before Patricia could explain that groundbreaking was a metaphor rather than architectural guidance, Brad from sales materialized at the construction site with the supernatural timing that sales personnel develop when they sense opportunity approaching at relativistic speeds. "This is perfect," Brad announced, his enthusiasm radiating at frequencies that made nearby birds confused about magnetic north. "We've accidentally invented the world's first consumer-focused observatory." "Brad, it's upside down," Patricia explained patiently. "The telescope is pointing into the ground. It can observe dirt, very expensive dirt, but still dirt." "Exactly. Think about it. Everyone's always looking up at the stars, but nobody's paying attention to what's directly below them. We'll market it as the Cosmic Selfie Observatory. Finally, an astronomical instrument that focuses on you." The square-haired boss appeared as if summoned by the mere mention of untapped market potential, his hair maintaining perfect cubic geometry despite the gravitational confusion emanating from the inverted structure. "Brilliant," the boss declared. "We'll revolutionize personal astronomy. Instead of making people feel cosmically insignificant by showing them the vast universe, we'll make them feel like the center of everything by literally pointing a telescope at their feet." "But sir," Patricia protested, "this completely defeats the purpose of astronomical observation. We can't study dark matter by looking at parking lot asphalt." "Who says we can't?" Brad countered. "Dark matter is everywhere, right? Including in asphalt. We'll be the first company to offer terrestrial dark matter detection services. Plus, think of the social media potential. #MyFeetFromSpace, #GroundSelfie, #Astronomically, me." What followed was the most ambitious attempt at architectural correction in QIS history. Patricia coordinated a massive crane operation to literally flip the entire observatory, while Brad simultaneously live-streamed the process as the world's first interactive astronomical realignment experience. The crane operators, working with the precision of cosmic surgeons, managed to lift the 200-ton structure and begin rotating it toward its proper orientation. For a brief, beautiful moment, the observatory hung suspended in perfect balance between Earth and sky. That's when quantum reality stepped in to remind us that buildings, like cats, can apparently exist in more than one orientation until someone signs the structural compliance form. The observatory began existing in a superposition of right side up and upside down simultaneously. Visitors could observe both the depths of space and the depths of the parking lot at the same time, leading to what the physics department called revolutionary multi-dimensional astronomical experiences, and what the insurance department called an actuarial nightmare requiring interdimensional liability coverage.
Ouch!
Well, Patricia sighed, watching tourists take pictures of themselves looking both up and down through the quantum superposed telescope. At least we're definitely observing something that's never been observed before. Brad, already designing merchandise for the Schrodinger's Observatory gift shop, nodded enthusiastically. And the best part? We can charge admission for both the Sky Tour and the Underground Tour. It's like getting 2 observatories for the price of one catastrophic construction error. The square-haired boss, his hair now displaying non-Euclidean angles in response to the quantum architecture, signed off on the project. Sometimes the best innovations come from the most spectacular mistakes. Though next time, maybe we should build our observatories in a universe with more straightforward spatial dimensions. And so, dear listeners, as we close the quantum construction site for another day, remember, in the vast architectural cosmos of existence, sometimes the most profound observations come from looking in the direction you never intended to look. Though I should note that the Cosmic Observation and Reality Verification Observatory now requires visitors to sign a waiver acknowledging that simultaneous observation of celestial and terrestrial phenomena may cause existential vertigo and paradoxical neck strain. And that brings us to the fascinating science behind why astronomers spent decades looking for something they couldn't see, only to realize it was everywhere they weren't looking. Now that we've seen how even accidentally inverted observatories can lead to revolutionary discoveries, let's talk about the Swiss astronomer who made the most important discovery in cosmology while being completely ignored by his colleagues for nearly 4 decades. In 1933, Fritz Zwicky was doing what astronomers do best, staring at distant objects and making calculations that would give accountants nightmares. His target was the Coma Cluster, a collection of over 1,000 galaxies located roughly 320 million light-years away, which sounds impressively distant until you realize that in cosmic terms, it's practically our next-door neighbor. Zwicky was applying something called the virial theorem, essentially a cosmic accounting method that relates the kinetic energy of moving objects to the gravitational potential energy holding them together. Think of it as the universe's way of balancing its books, except instead of quarterly reports, you're calculating whether galaxy clusters should exist at all. The math was straightforward. Zwicky measured how fast the galaxies in the cluster were moving, calculated how much visible matter they contained, and then determined whether there was enough gravitational attraction to keep the whole system from flying apart like a cosmic explosion in slow motion. The results were problematic. The galaxies were moving far too fast, about 10 times faster than they should have been, if only the visible matter was providing the gravitational glue. It was like discovering that all the cars on a highway were traveling at 600 miles per hour, but somehow staying in formation without any visible road signs or barriers. Zwicky, being a methodical Swiss astronomer with a healthy respect for mathematics, concluded that there must be additional matter in the cluster, matter that wasn't visible but was definitely there, exerting gravitational influence. He called this mysterious substance Dunkel Materie, German for dark matter. Not because it was necessarily black or sinister, but because it didn't emit, absorb, or reflect light in any detectable way. The scientific community's response to Zwicky's discovery was underwhelming. For decades, his colleagues essentially patted him on the head and suggested he check his calculations again. It was the academic equivalent of presenting a revolutionary business plan only to have the board of directors recommend you try turning your computer off and on again. This dismissal wasn't entirely unreasonable. Zwicky was proposing that 90% of the universe's matter was invisible and undetectable by any known means, rather like claiming that most of your company's employees are actually ghosts who show up to work but can't be seen, heard, or measured. yet somehow still get things done. It was a radical claim that required extraordinary evidence, and Zwicky's single study of one galaxy cluster wasn't quite extraordinary enough for the astronomical establishment. So, for nearly 40 years, dark matter remained a curious footnote in cosmology textbooks, an interesting idea from that eccentric Swiss astronomer who insisted the universe was mostly invisible. Meanwhile, astronomers continued building bigger telescopes to see farther into space, completely unaware that they were missing 85% of everything that existed. The transformation from ignored hypothesis to confirmed reality required someone with the patience to measure galaxy after galaxy, the precision to detect subtle rotational patterns, and the persistence to convince a skeptical scientific community that the universe really was far stranger than anyone had imagined. That someone was a soft-spoken American astronomer who would spend her career proving that Fritz Zwicky had been right all along, even though she initially had no intention of revolutionizing our understanding of the cosmos. She just wanted to understand why galaxies spin the way they do. When we return from this brief cosmic accounting break, we'll explore how Vera Rubin transformed dark matter from a theoretical curiosity into the foundation of modern cosmology, and discover how the telescope named in her honor will use technology Zwicky could never have imagined to map the invisible scaffolding that holds the universe together. Welcome back, my invisibly influenced investigators. Now let's dive into the remarkable story of Vera Rubin, the astronomer who transformed Fritz Zwicky's ignored hypothesis into the foundation of modern cosmology. Vera Cooper Rubin was born in 1928 in Philadelphia, and from an early age she was fascinated by the night sky. As a 10-year-old, she built her own telescope and spent hours tracking the movement of stars across her bedroom window. Her father, recognizing her passion, helped her join amateur astronomy clubs, though it's worth noting that in the 1940s, many professional astronomical societies still didn't admit women as members. When Rubin applied to Princeton's graduate astronomy program in 1948, she was told that women were not permitted in the program. Princeton wouldn't admit women to its astronomy department until 1975, a full 27 years later. Instead, she attended Cornell, where she completed her master's degree, and later Georgetown University for her PhD. Throughout her early career, she faced the kind of systematic exclusion that would be career-ending for most people, but Rubin possessed what can only be described as the intellectual equivalent of dark matter, an invisible but undeniable gravitational pull toward astronomical discovery. The discrimination was both subtle and overt. When Rubin became the first woman allowed to use the Palomar Observatory in California in the 1960s, there were no women's restrooms at the facility. Rather than let this stop her, she simply made her own sign and taped it over the men's room door. It's a perfect metaphor for her entire career. When institutional barriers blocked her path, she found ways around them with a combination of practicality and quiet determination. Rubin's breakthrough came in the 1970s when she teamed up with instrument maker Kent Ford to study the rotation patterns of spiral galaxies. Their plan was straightforward: measure how fast stars orbit around galactic centers at different distances, just as we can measure how planets orbit our sun at different speeds depending on their distance. The physics seemed obvious. According to Newton's laws, Objects farther from a gravitational center should orbit more slowly. Just as Neptune takes 165 years to orbit the Sun, while Mercury zips around in just 88 days. Applied to galaxies, this meant that stars near the galactic center should move faster than stars at the outer edges, creating what astronomers call a Keplerian decline in the rotation curve. Rubin and Ford expected to see this gradual slowdown. Instead, they discovered something that shouldn't have been possible. Stars throughout the galaxy were rotating at roughly the same speed, regardless of their distance from the center. It was as if every planet in our solar system, from Mercury to Neptune, were somehow completing their orbits in exactly the same amount of time, a violation of everything we understood about orbital mechanics. The implications were staggering. For galaxies to maintain these flat rotation curves, there had to be additional mass providing extra gravitational force, mass that extended far beyond the visible edges of the galaxy itself. Not just a little extra mass, but roughly 10 times more matter than what telescopes could detect. Rubin and Ford didn't initially set out to prove the existence of dark matter. They were trying to understand galactic rotation as part of broader studies of cosmic structure. But as they measured galaxy after galaxy, eventually studying over 200 spiral galaxies, the same impossible pattern emerged repeatedly. It was like being a quality control inspector and discovering that every single product coming off the assembly line violates the laws of physics in exactly the same way. What made Rubin's work so compelling wasn't just the discovery itself, but the methodical, undeniable nature of her evidence. Where Zwicky had studied one galaxy cluster and made a brilliant deduction, Rubin and Ford provided a systematic survey showing that the dark matter phenomenon wasn't an isolated cosmic oddity. It was the norm. Galaxies weren't just occasionally behaving strangely, they were all behaving strangely in exactly the same way. The astronomical community couldn't ignore Rubin's findings the way they had dismissed Zwicky's. Her rotation curves were reproducible, her methods were sound, and the implications were impossible to explain away. Either Newton's laws broke down on galactic scales, or the universe contained vast amounts of matter that interacted gravitationally but remained completely invisible to our instruments. This is why the Vera C. Rubin Observatory bears her name. The telescope isn't just honoring a distinguished astronomer. It's named after the person who transformed our understanding of cosmic structure itself. Rubin demonstrated that the universe we can see is merely the luminous tip of a vast, invisible iceberg. Her work revealed that galaxies are embedded in enormous halos of dark matter that extend far beyond their visible boundaries, like cosmic scaffolding holding the observable universe together. But there's another reason the telescope naming is particularly appropriate. Throughout her career, Rubin was an inspiration for women entering science at a time when the field was overwhelmingly male-dominated. She became a mentor and advocate, proving that groundbreaking discoveries could come from astronomers who had been systematically excluded from the profession's inner circles. A telescope designed to study invisible matter, named after a scientist whose contributions were often invisible to the astronomical establishment, has a beautiful symmetry that even the universe's sense of irony would appreciate. Now, let's explore the technological marvel that carries Rubin's name, and we'll spend the next decade hunting for the dark matter she helped discover. The Vera C. Rubin Observatory represents a quantum leap in capability. Yes, I know quantum is supposed to mean tiny, but we're reclaiming the phrase like a particle reclaims its uncertainty. At its heart sits the largest digital camera ever constructed, a 3.2 gigapixel monster that weighs as much as a small car and contains enough sensors to photograph the entire visible sky in exquisite detail every few nights. To put this in perspective, if you wanted to display a single image from this camera at full resolution, you would need 378 4K TV screens arranged in a grid. Each image contains so much data that if you printed it at normal photograph resolution, it would be the size of a basketball court. The camera produces so much information that the observatory will generate approximately 20 terabytes of data every night, equivalent to the entire contents of your laptop being replaced with new information every evening. The camera sits at the focus of an 8.4-meter mirror that's nearly 28 feet across, making it one of the largest single mirrors ever cast for astronomical use. But size isn't everything. It's the combination of the mirror's light-gathering power with the camera's unprecedented field of view that makes the Rubin Observatory revolutionary. While most large telescopes focus on tiny patches of sky in exquisite detail, Rubin will photograph enormous swaths of the heavens, covering an area equivalent to 40 full moons in a single exposure. This wide-field capability enables what astronomers call the Legacy Survey of Space and Time, or LSST, a 10-year program to photograph the entire southern sky every 3 nights. Think of it as creating a time-lapse movie of half the universe, capturing everything from nearby asteroids to the most distant galaxies. Every object in the survey will be photographed hundreds of times, allowing astronomers to study how the cosmos changes over time with unprecedented precision. The telescope's primary mission is dark matter archaeology, using gravitational lensing to map the invisible scaffolding that shapes cosmic structure. When light from distant galaxies passes through regions of concentrated dark matter, the dark matter's gravity acts like a cosmic lens, subtly distorting the galaxy's images. These distortions are incredibly small, typically less than 1% changes in galaxy shapes. But when measured across millions of galaxies, they reveal the distribution of dark matter throughout the universe. It's rather like trying to map an invisible maze by watching how a flashlight beam bends as it passes through. You can't see the walls directly, but by carefully measuring how the light curves, you can reconstruct the entire structure. Rubin will perform this cosmic cartography on an unprecedented scale, creating 3-dimensional maps of dark matter distribution across billions of light years. But dark matter is just one of Rubin's scientific targets. The observatory will also study dark energy, the mysterious force causing the universe's expansion to accelerate. By measuring the distances and properties of Type 1a supernovae across cosmic time, it will discover and track potentially hazardous asteroids in our solar system, providing an early warning system for objects that might threaten Earth. And it will revolutionize time-domain astronomy, detecting everything from stellar explosions to gravitational wave sources to exotic phenomena we haven't yet imagined. The observatory's approach differs significantly from other major dark universe missions like the European Space Agency's Euclid Space Telescope. While Euclid operates from space with the advantages of perfect seeing and no atmospheric interference, Rubin leverages the benefits of a ground-based facility, larger mirrors, easier maintenance, and the ability to upgrade instruments over time. The two observatories are brilliantly complementary. Euclid provides the high-precision, space-based measurements needed to understand dark energy's properties with exquisite accuracy. Rubin provides the wide field, time-domain observations needed to discover new phenomena and track cosmic evolution over unprecedented scales. Together, they represent humanity's most ambitious attempt to understand the 95% of the universe composed of dark matter and dark energy. A cosmic detective story that began with Fritz Zwicky's puzzling calculations and Vera Rubin's revolutionary observations. But perhaps the most profound aspect of Rubin's dark matter hunt is how it connects to broader questions about the nature of reality itself. Dark matter isn't just a cosmological curiosity. Its properties may hold keys to understanding quantum gravity, the unification of fundamental forces, and the ultimate fate of the universe. If dark matter consists of particles predicted by supersymmetry, detecting their cosmic distribution might illuminate paths toward unifying physics' awkward roommates, gravity and quantum mechanics, who still won't speak to each other after the Big Bang Christmas party. If dark matter interacts through previously unknown forces, those discoveries could reveal entirely new sectors of physics. And if dark matter's behavior changes over cosmic time, it might tell us whether the fundamental constants of nature are truly constant or whether reality itself evolves in ways we haven't yet imagined. In essence, the Rubin Observatory will use gravitational lensing to perform archaeology on the invisible universe, reconstructing the cosmic skeleton that has guided 13.8 billion years of cosmic evolution. It's humanity's most ambitious attempt to understand the 95% of reality that remains hidden from our instruments. A quest that began with Fritz Zwicky's puzzling calculations and will culminate with the most detailed map of cosmic structure ever created, all in honor of the astronomer who proved that the universe is far stranger and more wonderful than we ever dared imagine. Well, my cosmically concealed colleagues, we've reached the end of another quantum investigation into the invisible. Today we've learned that in the multiverse of astronomical discovery, every breakthrough exists in a superposition of revolutionary insight and completely obvious in retrospect, until a brilliant scientist collapses the wave function into actual understanding. Perhaps most profoundly, understanding dark matter might force us to confront the limits of human perception and the assumptions built into our scientific methods. We've constructed our entire understanding of the universe based on the small fraction of reality that interacts with light. What other fundamental aspects of existence might we be missing simply because they don't happen to emit photons in wavelengths our instruments can detect? The Rubin Observatory represents humanity at its most audacious, building a technological marvel in one of Earth's most remote locations to photograph invisible cosmic architecture across billions of light years and 10 billion years of cosmic time. It's a testament to our species' remarkable ability to ask questions about things we cannot see, cannot touch, and can barely imagine, then spend decades developing the tools to find answers. Standing here at the foot of this gleaming white dome in Chile's Atacama Desert, I'm struck by the continuity of human curiosity. Fritz Zwicky used pencil and paper to deduce that galaxy clusters contained invisible matter. Vera Rubin used photographic plates and careful measurements to prove that galaxies were embedded in dark matter halos. Now, their intellectual descendants will use 3.2 gigapixel cameras and quantum sensors to map the invisible scaffolding that shapes cosmic destiny. In the end, the Vera C. Rubin Observatory embodies both humanity's greatest strength and our most persistent limitation. Our strength lies in our refusal to accept that invisible means unknowable. Our willingness to spend decades developing increasingly sophisticated ways to detect the undetectable. Our limitation is the humbling realization that after mapping dark matter's cosmic web, we'll likely discover that the universe contains even stranger and more wonderful mysteries we haven't yet learned to detect. So as this remarkable telescope begins its cosmic survey, remember that we're not just hunting for dark matter. We're participating in humanity's ongoing conversation with the universe, asking questions that previous generations couldn't even formulate. And somewhere in the vast expanse of space-time, the invisible architecture that holds reality together continues its ancient dance, waiting patiently for us to finally understand the cosmic choreography that's been surrounding us all along. The universe's greatest mystery is about to meet humanity's greatest telescope. The only certainty is that the answers we discover will be stranger, more beautiful, and more humbling than anything we currently imagine. Help us map the dark matter of podcast preferences. We've launched a brief listener survey to understand what cosmic topics fascinate you most and how we can improve your multiversal employee experience. Find the survey link in our show notes, because unlike dark matter, your opinions are definitely detectable and absolutely matter to us.
The Multiverse Employee Handbook was created by Rob Corrigan. The host, David, is a professional voice actor who has digitized his voice through 11 Labs voice cloning technology. All episode thumbnails are created with OpenAI, and music and sound effects come from Pixabay, which are generated by human artists. Everything else, the writing, jokes, research, sound editing, and coffee consumption, is 100% human-made by a human. No cats are harmed in the making of this podcast. Visit our website for more information about the Multiverse Employee Handbook.